Yeah, thank you. Good afternoon, everyone. I'm Giulia LURAGHI, and the work that I'm presenting today was conducted by Anna Ramella and Elena Rodelli during their master thesis with me and Francesco Migliapacca as supervisors. And this work was done in collaboration with the Ospedale Politecnico of Milano with Professor Santi Trumarchi. The aorta, as you know, is the largest artery in our body and is composed by the ascending part, which connects the upper part of the left ventricle, the aortic arch with the 3 branches, and the descending aorta, composed by the thoracic and the abdominal segments. The main pathologies affecting the aorta are the aneurysm and the dissection. The aneurysm is an enlargement of more than 50% of the nominal normal diameter of the lumen and is almost asymptomatic. The dissection occurs when there is a laceration of the intima, which creates a false lumen between the intima and the media. Blood can flow with this pathology in both the true and the false lumen. These pathologies can be treated with the open standard surgery, but also with an endovascular, minimally invasive procedure called thoracic endovascular aortic repair, TEVAR. These techniques consist in the insertion through the femoral arteries of a catheter with the crimped device. Once the device is placed in the location of the pathology, in the aneurysm, as you can see from the picture, or in the dissection area, it is deployed by unsheathing the catheter. And in this way, the nominal and true lumen is restored. In the short term, there is no complication, but in the long term, different complication can occur due to the presence of the device in the aorta. For example, the endoleak, which is blood flow in the pathological region, the migration of the device, which is more than 5 or 10 millimeter, the burr beak, which occur due to device malposition, and finally the compliance mismatch, because the difference in stiffness between the aorta and the device. The device is composed by a graft and a stent. The stent is made of a shaped memory alloy. Regarding the literature of the numerical work on this the TEVAR technique, there are a lot of finite element analysis which only study the structural mechanics of the device and of the interaction between the device and the aorta to reproduce exactly the clinical procedure. On the other hand, there are CFD analysis to study the hemodynamics of the aorta after the clinical procedure. But the novelty of this work is because we use a strong couple fluid structure interaction simulation to model at the same time the hemodynamics and the structural mechanics of both the pre and the post procedure. So this work, the aim of this work is the development of a numerical workflow to model the TEVAR procedure. So to implant the device in a aorta, for now idealized aorta, and in order to reproduce the pre and post scenario of this idealized patient. We start with a structural finite element analysis to model the crimp, the morph, and the deployment of this device. And then we moved to fluid dynamics analysis to study the pre-TEVAR and the post-TEVAR. We obtain the post-TEVAR configuration from the deployment structural analysis. And we compare a CFD simulation with a FSI simulation. Regarding the structural finite analysis, we start performing a mesh sensitivity analysis by create 3 different grids for the stent, as you can see from the picture, with 3, 4, and 5 elements in the thickness of the stent. The finite element chosen were 3D hexahedral elements with reduced integration with pulsar hourglass control. And the material was a shaped memory alloy to mimic the nylon properties of the stent. And regarding the mesh sensitivity analysis, we choose the displacement of the stent as a primary variable and the von Mises stress as second integrated variable. As you can see, the error of the first grid was less than 1% with respect to the finer grid, and so we choose the 3 elements grid. Regarding the graft, we model, we discretize the graft with a 2D triangular shell, as you can see from the picture, and we connected the graft and the stent with a node-to-node connection. We model the material of the graft with a linear elastic material law. We perform, as you can see on the right, the crimp and free release simulation of this only of the stent and then of both the graft and stent. Finally, we have the aorta. We have this aorta geometry from literature, and we discretize with quadrangular full integrated shell elements, and we use uncompressible hyperelastic material, the Munir-Rivlin material law, to model the soft material of the aorta. For this simulation, we use a commercial software named LS-Dyna, which is part of the ANSYS packet. It's a finite element solver, and for this case, we use the explicit solver. The time step of this simulation is very slow, as you can see, because we use a mesh scaling technique. The device is crimped morphed using some rigid cylinder to mimic the catheter, and we use the soft penalty-based contact between the device and the aorta. So here you can see the movie of this simulation. And we can see as a result of the simulation different aspects. For example, the contact force. You can see here the contact force where the device is in contact with the aorta, the distance between the device and the aorta wall, and finally also the von Mises stress on the aorta. You can see that the device is in contact only in the proximal and distal regions. Then we move to the CFD and FSI simulation. We perform a hemodynamics analysis of the pre-TEVAR, so with only the aorta, and about the post-TEVAR situation, with keeping the final configuration of the structural simulation as a starting point to our domain. In particular, regarding the FSI algorithm, we choose a two-way, strong couple, and boundary-fitted FSI simulation. We use for both the structural and the fluid an implicit solver, finite element solver, We use the incompressible CFD solver, which is a package already implemented in the LS-DYNA commercial software, and the explicit finite element method to model to solve the structural part. We use the same time step for the two domain, and the fluid domain as a HELA ALE approach, while the structural classical Lagrangian approach. Just to give you an idea about the computational time, for the FSI simulation, we use 20 CPUs, and with only the aorta, the simulation lasts 40 minutes, while for the complete device and the aorta, FSI simulation, 12 hours. Regarding the fluid domain, we use a boundary layers technique to discretize the blood domain. The blood was modeled with a Newtonian fluid, and we simulate 2 cardiac cycles. You can see some details of the mesh, and on the right, the boundary conditions. So you apply a flow rate at the inlet, and at the 4 outlet, the 3 branches, and the descending aorta outlet, the 3 elements Wien-Kessel boundary condition with parameters from literature. Regarding the structural domain, the inlet and outlet were constrained in all the direction, and from the structural simulation, we export not only the configuration, but also the stress and strain. We perform a slight smoothing operation on the graft to create, in order to create a proper fluid mesh grid. As a result, we first want to compare the CFD and the FSI simulation in the post-TEVAR scenario. So you can see on the left the CFD with rigid wall, and on the right the FSI simulation with hyperelastic material for the aorta and shape memoralloy material for the stent and linear elastic material for the graft. Here is a picture from the systolic peak, and we can say that in the FSI simulation the velocity field was lower in the systole, as you can see, and also the pressure field was lower. You can see from the curves. The curves are all results from the Wien-Kessel boundary applied boundary condition. So we can conclude from this part, from this comparison, that the FSI analysis is necessary to take into account all the model deformability in this application. Now we want to compare FSI simulation regarding the pre and the post TEVAR. We can see that in the post TEVAR, the velocity is higher. The same for the pressure, especially at the inlet and the 3 branches pressure. In particular, with the complete FSI simulation, we can check and calculate, evaluate some complication of the procedure. Regarding the endo leak and the burr beak, we can calculate the flow rate in the device and also out the device, so between the device and the aorta wall. And we can see also from picture of the section number 1 that there is some burr peak, because you can see that there is some malapposition in this part of the aorta. Also, we can evaluate the device migration, so we can calculate the displacement force with this formula, and calculate the global direction of the device migration force. Notice that this vector doesn't change the direction during the cardiac cycle, because the pressure in this formula, the shear could be ignored, and so the pressure the same direction. And this value is confirmed by literature study. Lastly, we can measure the compliance mismatch because we can calculate the compliance in the pre-TEVAR, so with the only aorta, and in the post-TEVAR, so with the device deployed in different sections. And with this formula, we can also calculate the error. And we can see that the error at the end, so in section number 4, so in the distal part of the device is almost 0, and the bigger error is exactly in section 2, so in the proximal part of the device. And this is confirmed by literature study again. So this numerical tool, so the FSI simulation can be used both in the procedural planning, but also in the stent graft design optimization. We use an idealized aorta and Wing-Kessel boundary condition, and this was easy for us because we need to, at the beginning, to develop the methodology, but then now we can move to patient-specific cases. So the novelty of our work is the complex of the FSI simulation with the device embedded in the fluid domain, the Wing-Kessel boundary condition, nonlinear materials, and the contact. And this, with this complex simulation, we can evaluate all the main complications of this procedure. The future developments of this study is to validate the simulation. So we are working on this.
3 minutes and then
yes. And also to include the pre-stress configuration, the zero stress configuration of the aorta, and try to apply to real patient-specific case. As you can see here, we start working on this with an aneurysm patient, and also, with dissection patient. And thank you for the attention.
Thank you, Giulia. We have time for 1 or maybe 2 questions from the audience. Okay, in the meantime, I have a curiosity. So thanks for this very detailed analysis of your the dynamics of TEVAR. I would like to ask you, you maybe mentioned just in the last slide, if you consider, let's say, an aorta with huge tortuosity, okay? Do you think that your method could be easily adapted, or you will need some, I don't know, modification in the algorithm for the deployment or CFD? I don't know.
Okay, thank you for the question. And yes, I think that the tortuosity of the aorta, we can manage this with the morphing option to crimp and to release the device. So yes, I think it's easily addressed with the technique that we use to crimp, because we start to draw some cylinder from a strain cylinder, as you can imagine here, and then we obtain a morphed cylinder here with a smaller diameter, and then we obtain all the intermediate configuration, and then we use a morphing option to crimp and at the same time to morph the device. So yes.
Okay, thank you. Just a very quick, if there are no other questions, the parameters, the 0D lumped parameters were the same for the pre and post TEVAR, or there is a reason to adapt them? I don't know. I don't know if it is.
No, we use exactly the same with parameters from literature, because
there is no reason to differentiate. Okay. Thank you, Giulia LURAGHI.
You're welcome.
And okay, we can pass to